Okay, ladies and gentlemen, today we are going to continue or start with chapter 4 in the textbook of Cengel and Ghajar, and the chapter is about transient heat conduction. But before we get into the details of the chapter, I just want to go back a little bit and give you a better picture of heat transfer, where this part fits into the bigger picture, and to do a little bit of revision of previous work. Okay. So previously, you've already done it. You've seen that heat transfer, that there are three different modes of heat transfer. First mode is conduction, then it is convection, and then radiation. Three different modes of heat transfer. Okay. Now the conduction you've done in chapter 1 of the textbook and in chapters 2 and 3. Okay. Convection you didn't do that much. You've already done chapter 1, which was just an introduction, telling you about the heat transfer coefficient. And then in this course, there are a few more chapters, which are chapters 6 to 9 on convection heat transfer. And we're also going to do that. And then there's radiation heat transfer again. You've touched on it in chapter 1, but it is covered in more detail in chapters 12 and 13 in the textbook. Okay. Now, transient heat conduction, this chapter, sort of falls in between conduction and convection, in between them. So chapter 4 is transient heat conduction, sort of overlapping between the two. And that is the reason why I just want to go back to conduction and a little bit to your fluid mechanics course and do a little bit of revision. But let's just quickly revise the most important principles and equations for conduction heat transfer, convection heat transfer, and radiation heat transfer. For conduction heat transfer, you have learned that the heat transfer rate for conduction, okay, is equal to minus K multiplied by an area multiplied by dt dx. Do you remember that equation? Okay. Which is called Fourier's equation. Okay. Fourier's equation, the conduction heat transfer is equal to minus K, the area multiplied by dt dx. K is the thermal conductivity, A is the area, and X would be the distance over which we have a temperature gradient. Okay. Now, this is the one-dimensional equation. Okay. In these chapters, in chapters 2 and 3, the conduction equation was also derived in 3 dimensions, which is called the general heat conduction equation in chapter 2. And this equation looks like this: partial ddx of K partial dt dx plus partial ddy of K partial dt dy plus partial ddx of K partial dt dz plus E gen is equal to rho C partial dt dt. But we've got two T's here, one for temperature and one for time. Okay, so this is the general heat conduction equation in 3 dimensions. The x direction, the y direction, and the z direction. E gen would be energy which is being generated inside the medium. It might be an electrical resistance element where we put in some watts, or it might be a nuclear reaction or a chemical reaction. Okay, so this is heat which is being generated on the inside, and the units of that thing, if you don't remember, is watts per square meter. So how many watts per square meter is generated inside the body that has been considered? Obviously, capital T is the temperatures, small t is time, okay? And this time is what this chapter is all about. So it is, how does things change as a function of time? Most of the problems that you've done up to now, we've said that is equal to 0, which means it is steady state. Steady, there are no changes as function of time. So steady means partial dt is equal to 0. And if it's unsteady, then in general, we are interested in the temperature gradient or the temperature values, not only at different positions, but also as a function of time. Okay, now, with this equation, you theoretically should have the ability for any body, okay, this is now a body, and theoretically, you should be able to solve the temperature on inside of the body, okay? As long as you've got the boundary conditions, okay? As long as you have the conditions at time equals 0, theoretically, you can get the temperatures as function of time, okay? Now, if I would now take your cell phone and I would say, well, here's your cell phone, go and solve me, and throw that cell phone of yours in water at 0 degrees Celsius. I want to see in your cell phone as a function of time how the temperature decreases. Okay, how are you going to do it? Well, you've got a few options. The one is you can go and do it yourself, really. You can try to do measurements. So that's that one way that you can do it. The other obvious way would be, well, let me look at the equation. I've got an equation, so why don't I solve it? There's a little bit of a problem, and that is that we still need another Einstein or two to do that. Okay, so a general analytical equation is not yet available for the energy equation or for the momentum equations, especially in 3D as a function of time. So if you can do that, then most probably you'll get the Nobel Prize for. Okay, so it hasn't been done yet, so we can't do it. We can do it with CFD, as you know, and you're going to do a CFD course now, so you can discretize it, or you can do it with finite elements, it doesn't matter. Discretize it in a grid, and then discretize the equations, and then there are different procedures that you can follow to solve the equations. The reason is, you can't always do it because it takes a lot of time, in most cases, and your time in industry is going to be very valuable to your organization and to clients. So in many cases it is very, very important to quickly be able to get an answer. Okay. So the third approach that can be used as well, and that is a good engineering approach, is to say, well, let's start simple. We try to make things as simple as we can. So we do not say it is a three-dimensional body, so we throw away that term and that term. Okay. We say that K is a constant, the thermal conductivity is a constant, nothing is being generated on the inside, and we say, well, let's first start with throwing away that term, and then we've got that equation, and then we can start solving practical problems. Okay? And then slowly we can start making it more complicated. And there are sort of solutions available for simple type of geometries, either steady state and for unsteady. Okay, but it took people years and years of mathematics trying different things before they could solve it. It's a lot of work, and it is very complicated. Okay, so this is sort of the path that we're going on to, except for one thing, and that is that at the moment with that equation, the heat transfer coefficient on the outside, you can't really take it into consideration. You can, I'll show you later on how to do it, but at this stage, you can't really if you just look at that equation. Okay, so the next the next category of problem is obviously convection heat transfer. Okay, convection heat transfer is equal to the heat transfer coefficient multiplied by the area multiplied by the surface temperature minus the temperature of the environment. It is the simplest of all the equations, but it is also the most complicated because getting that heat transfer coefficient is very, very difficult. It's not so easy. There's no analytical solution that can do that at the moment. We have to do experiments to get it. And then we can use the experiments, give the results in tables or graphs for other people to use. Okay, so that is the convection heat transfer, and then the last one is radiation heat transfer. Okay, radiation heat transfer is energy emitted in the form of electromagnetic waves or photons. Typically in a vacuum, it happens at the speed of light, and the radiation heat transfer equation is written as the emissivity multiplied by the Stefan-Boltzmann constant multiplied by the surface area multiplied by the surface to the 4th power minus that of the surroundings to the 4th power. Okay, so that is the radiation heat transfer equation. Right. Now that we've done a little bit of revision, I want to go back to fluid mechanics. Fluid mechanics, when we've analyzed fluid motion types of problems. Okay, now I want you to divide your page in two, a left-hand side and a right-hand side in terms of the columns. You would have maybe realized that there are two approaches that can be used to solve fluid motion types of problems. The one is with so-called integral relations. Okay, integral relations. And the other approach is to use differential relations or equations. Okay. Now, when do we use an integral approach and when do we use a differential approach? Just to give an example, in chapter 3 in white, you could have solved maybe for a rocket with a certain muzzle. Okay. You wanted to determine the outlet velocity through the nozzle. And you could have done that by putting a control volume around the rocket. Okay. And then there were equations like the continuity equation, the energy equation, and the momentum equation, which were all integral types of relations. Okay. Now, because I do not have enough space here, I would like to write this equation, the continuity equation. I'm going to write it here, but it should be here on the left-hand side. Okay, now this equation, the continuity equation, looked like this. It says the integral over the control volume of partial d rho dt. Take note, that is a volume. Okay, the V like that is volume, not velocity. Okay, volume plus the sum of the densities multiplied by the areas multiplied by the velocities, everything going out, minus the sum of the densities, the areas, and the velocities coming in is equal to 0. Okay. And that is the one-dimensional continuity equation, which should be in here. Okay. The one-dimensional continuity equation. For the differential equation, when do we use the differential equation? Well, with this same rocket, If I'm interested in knowing what happens at a specific place in the rocket or the velocity field, I would like to know in a control volume, small one, of dx, dy, and dz, I want to know the velocity at a specific point. With this approach, it wasn't possible. You could only solve what happens over the control volume. Okay, not on the inside in terms of detail. Okay, now with this one, the continuity equation looks like this. Partial d rho dt plus ddx, partial ddx of rho u is equal to 0. And again, take note, it is the one-dimensional equation. This one also, the one-dimensional equation. Okay. And there are similar equations for momentum and energy, and also for angular momentum. They're all in your textbook of White. And I hope you've used them, and you know how to use them. Now, I would like to continue here, okay? So, although I'm writing here, the idea is I'm continuing on this side of the column, okay? We're looking at the differential approach now, okay? Now, with the differential approach, you can also do the derivation of the continuity equation in 3 dimensions, not only in 1, okay? Then the equation looks like this. Okay, it's a continuity equation, and it's typically equation 4.4 in the textbook of White. And this equation looks like this: partial d rho dt plus partial ddx of rho u plus partial d dy of rho v plus partial ddz of rho w is equal to 0. Okay. So in the derivation of that equation, we've looked at that control volume, and we look at the velocities in the x direction, in the y direction, and in the z direction, going into and out of the control volume. Then, I'm still continuing here, there is the linear momentum equation. So again, now you put the pressures on both sides of the control volume, and we solve the momentum equation. Okay. And this equation is a little bit more complicated. It looks like rho like this. Rho multiplied by the gravity in the x direction. Okay. Because gravity doesn't always work downwards as we know it. If you're up in space, you know, things can change. So we have to take gravity into consideration in different directions. Minus partial dp dx, that would be the pressure difference over the control volume. And then there are many more terms, and they typically looks like this. The shear stress in the x direction, and many more of them that I'm not going to write down. And that equation is equation 435 in the textbook of White. Then we make a very, very important assumption, because this equation is difficult to work with. Okay. We make the assumption of that for the fluid, the shear stresses is linear in terms of the shear strain. And you've done that also. And if that is linear, we call it a Newtonian fluid. Remember that? It's Newtonian. Now, if we make this assumption in these terms, we can make the equation more simple. Okay. Okay, so if we make this assumption that it's linear, then we can get what we call the Navier-Stokes equations. Okay, the Navier-Stokes equations. I need some space, so I'm going to clean here. Okay, so the Navier-Stokes equations looks like this. Rho multiplied by the gravity in the x direction minus dp dx plus the viscosity multiplied partial d2u dx squared plus d2u dy squared plus partial d2u dz squared is equal to rho multiplied by partial du dt, and this t is now time. How things change as a function of time. And we are moving into what is going to happen in this chapter. We are interested in how the temperature changes as a function of time. Okay, now this equation is only in the one direction. We still have to write them down in the y and z directions. Okay, so in the y direction, it is rho multiplied by g in the y direction minus partial dp dy plus the viscosity multiplied by partial d2v dx squared plus partial d2v dy squared plus partial d2v dz squared is equal to rho multiplied by partial dv dt, where the t now is time. That is for the second direction, the y direction. We still have to do it in the z direction also, and that you can go and do at home. Okay, so it's very simple. It is partial d2v dx squared plus partial d2v dy squared plus partial d2v dz squared is equal to rho multiplied by dv dt in the three directions. Now that is the very simple case for a Cartesian coordinate system. You can do the same for a cylindrical and spherical. It becomes more complicated, of course. Okay. So in terms of the equation that we had previously, that is the momentum equation. Okay, so just coming back to this approach, remember we've got the integral approach with all the equations. I'm not going to write them down, you've done that last year. And then we've got the differential ones. With the differential ones, we've got the continuity equation, the linear momentum one, and now there's one missing, and that is the energy equation. So the energy equation, again, in all the assumptions, we make the very important assumption, again, it's for Newtonian flow, then the energy equation reduces to partial d dx of k partial dt dx plus partial d dy multiplied by k dt dy plus d dz of k dt dz plus E gen is equal to rho multiplied by c partial dt dt, and again where this t is now time. So that is the energy equation. Okay, and I see we are out of time, so we will continue with the rest of the work with the next lecture. Thank you very much, ladies and gentlemen.